So that's a rough outline. At the end, I'll give a very quick demo of some of the features in DynoChem resources that I refer to in the presentation, but I won't do any serious calculations in today's webinar. Just before getting into the technical meat, I want to say a couple of words about some of the leading contributors to mixing technology in the last 30 or 40 years who have really learned and shared a lot of the insights that we're going to touch on in today's meeting. I can't make a complete list. There have been a lot of contributors, particularly through the North American Mixing Forum over that period, but people that I'd like to name check are listed here. So Ed Paul, who was a chemical engineer at Merck from I think maybe the early 60s till the mid to late 90s, and when he joined Merck he noticed some unexpected mixing dependence on the outcome of some liquid phase reactions, and that wasn't something that was particularly expected either by practicing engineers or by academics at the time. And he started a PhD while working actually with Robert Trebal, who wrote the mass transfer book that a lot of us would have used in undergraduate Chem Eng, and really kind of started off the whole micromixing, mesomixing field of research. John Bourne, whose name many of you will also know, Professor Bourne, formerly of ETH Zurich, then began authoring in the 1980s a whole series of articles putting in place building blocks to help understand mixing, and particularly micromixing initially. I'll come on to what these terms mean in a minute, but also mesomixing in some of the later articles. And in our company we have the pleasure of having several people who got their PhDs under the guidance of Professor Bourne, and also worked a little bit with the next person on the list, Dr. Art Etchells from DuPont, who really for a comparable period has been applying mixing knowledge, fresh out of academia and out of research labs, to a whole plethora of applications at DuPont. And Art Etchells was always very good at feeding back the practical realities of the mixing problems that he observed and helping to guide the subsequent research to answer the important questions. Also, more recently, a major contributor in this area has been Jerzy Baldiga from Warsaw University in Poland, who particularly collaborated with Professor Bourne through maybe the late 80s and a lot of the 1990s, and allowed a lot of the computations of the models that have developed in this area to be carried out alongside the experimental work. And the final person I'll mention is Keith Carpenter, who's formerly with Zeneca but now at ICES in Singapore. And Keith is responsible for a lot of the insights that helped to bring this kind of knowledge into the fine chemicals and pharmaceuticals industries, and some of the more multi-phase aspects of what I'm going to talk about today. So, starting with so-called homogeneous liquid phase systems, there's a nice animation that we've been using for about 15 years now to explain mixing sensitivity and some of the terminology that arises in homogeneous liquid reaction systems. So I'm just going to spend a few minutes talking through that. And we use some little molecules, which I hope you can see at the top of your screen now. So we have a molecule B, to which we're going to add a reagent A. So it's A to B, and those two can react with a rate constant, chemical rate constant K1, to give a desired product, or that's the green molecule, that's the one that we want to make. But like a lot of practical industrial reactions, there is also the possibility that A, the reagent, which we have to add to make OR, can also react again with OR to make effectively a kind of a dimer, or an over-reacted product, in this case called S, which is indicated by the red sphere. So this is the kind of chemistry that I'm just going to assume right now for the remainder of the animations on this slide. And again, like a lot of these reactions, it wouldn't have made its way into development if the first reaction hadn't been much faster than the second. So K1, the rate constant of the desired reaction is much larger than K2, the rate constant of the side reaction. So that means that in the lab, under good mixing conditions, we normally make just the nice green material, and occasionally we might see a little bit of the red material, because the favored reaction is the main reaction. But under other conditions, it would be possible for us potentially to make a lot more of the unwanted red material. So a little bit about the kind of extremes of behavior that you see with this kind of system, even in a liquid phase system. So just miscible materials here coming together. So again, I'm focusing on the case where A is added to B, and there are two sides to the diagram I'm going to work through now. On the one side, on the left-hand side, we're going to look at what happens when the mixing time is much less than the reaction time. In other words, mixing is practically instantaneous. Mixing is complete before the reaction really is able to get going, and that is the way we want it to be in an awful lot of circumstances. And when reactions are slow, that's quite easy to achieve. But when the kinetics get more rapid, say in the minutes, tens of seconds, seconds type timescale for the kinetic speed, then this can be more challenging. So the left-hand side is when mixing is much faster than kinetics. So initially we have our material A, lots of molecules of A, bumping up against molecules of B, and then mixing happens rapidly. So we get a nicely randomized mixture of A molecules surrounded by B molecules and B molecules surrounded by A molecules. So mixing is now effectively complete in this kind of mental model, and then the A's and B's realize they're beside each other and they react chemically, and we get product R. And we just get the very occasional molecule of S because there happened to be a B or an A in the wrong place. So there was a local excess which caused formation of the overreacted product. So if you can imagine, you do a fantastic job with mixing. All the mixing is complete long before the kinetics really get started. Then you would make in the limit no S at all. So the fraction of S that you make from this reaction scheme, the selectivity for S, if you like, or the percentage impurity, would be zero, or would tend to zero, very close to zero in the limit. So that's the kind of happy path, the situation that we want to achieve in general. And like I say, it's relatively easy to achieve that when the kinetics are not too rapid. The other extreme, which is when mixing time is much longer than the kinetic speed of the reaction, the kinetic reaction time. Again, we initially start with our two streams coming together, but now, because there isn't enough intense contact between the A and B materials, there's just a small amount of contact area between them, and A and B molecules react with each other because they're beside each other, but they don't get randomized throughout the rest of the mixture quickly enough, so the A molecules go on and react with the R molecules to make S molecules. So in this case, where mixing is slower and in the limit much slower than the kinetic reaction time, we make a lot of S. It's potentially possible for us to make 100% or practically 100% S if the mixing is poor enough. So those are the kind of qualitative extremes that you get. On the left you have kinetics limiting, and that's very often the kind of assumption that synthetic chemists will make, development chemists potentially even when scaling up, that kinetics are limiting. And in that case you would see very little in this case of the impurity. And at the other extreme you have mixing being completely rate determining, in which case potentially the amount of the overreacted product tends to 1. And as you might expect, there is an intermediate region, the so-called mixing sensitive region, or where the kinetics are neither slow relative to mixing or instantaneous relative to mixing, but just fast relative to mixing. So when we throw around terms like slow and fast, we really mean, compared to mixing. Is it a fast reaction compared to mixing, or is it a slow reaction compared to mixing? It's kind of a relative term. So yeah, in between those extremes of behavior where you have intermediate levels of mixing, then you would see a percentage, in this case, of the red material somewhere between 0 and 1.